What on earth was that, you ask? Well, that was VGM. Welcome to another Hopper video. I'm going to talk about how we were playing these retro music on our little 6502 machines. And specifically, if you go to VGM rips and you look under systems, and then you look for the PC Junior, what's it called? No, Tandy 1000. And this is game music, from the 80s and 90s. We're going to look at Lemmings. That's Mozart Sonata. Where is it there? It was from the Lemmings game. So, yeah, it's not the best Mozart, but it's pretty fun to listen to. Anyway, I had no idea that this existed until Dave Latham, who has his 6502 retro banked memory machine, bank ROM and bank RAM. So the specs of his machine, he's got like four 16K ROM banks, and then quite a lot of RAM. And he signed up. He's on our Discord channel, and he wanted to get Hopper working on his machine. So when he boots his machine, he can switch into different banks of ROM. So he can either launch with Wasmon or Basic, or launch straight into Hopper. So we got the Hopper runtime running on his 6502 machine. And then one of the pieces of hardware he has on his 6502 machine is he has this SN76489 sound generator. And he had experience with this. So it was him coming up with the player. And the challenge was to try and write this player in Hopper. Because Hopper's an interpreted language, so running Hopper interpreted language on a 6502 and still getting the timing right for this music is kind of a challenge. So the first thing we did, is how do we get the music on there? So we actually just hard coded it into the program in this constant array. And how do we do that? I wrote another program. Actually, Dave first wrote a Python version of this, and then I wrote a Hopper version. That's a converter that converts the binary format of VGM into a useful format that we can interpret. That's in hex, in a constant array. So the converter's command line arguments are that you just give it the path of the file you want to convert. How many Ks of the music do you want? And that's a tricky bit because you can't just chop it off. You have to chop it off at an instruction rather than at an argument of an instruction, because you'll just crash. And then I made a second version, which is binary. So instead of converting it to Hopper source code, this converts the VGM file to a stripped down binary version that we can use like I used that on the RP2040. Anyway, so that's how we make our music. We convert our music from the VGM format into something we can use in Hopper. This source code constant VGM data. So this is the converted data, right? And then to play it, he'd written a program initially, and then I used that as a sort of a educational example of how you could take advantage of certain of the features of the Hopper programming language to write a better player. What does better mean? I mean, easier to understand perhaps, and then also I tried to initially the timing. It's originally his code, the converter, and then so this shows you how it was also like it was a great example to show, let's do something useful on the SBC's parallel port here. Let's hook up one of these little sound chips, because obviously I don't have one of these built into my board, so I had to add it on as a little project. So in this Hopper code here, you can see how you would wire that up to your port. So you've got a write signal, and you've got a ready signal, and you've got the data signals and which pins they're on. And then these are the instructions of VGM that we support. So we don't need to support that many instructions to support the simplest music that's made for this really simple sound generator. And then in the main play loop of the program, this is the inner loop of interpreting the data in that array, so that the array would be here, and increasing the index as we go through it. And what I did here, initially this was a bunch of if statements, and then I showed how you do it with a switch statement, and then I showed how you would do it with an array of delegates. So function pointers. So we call these functions, and this is like the zippiest way you can do it. Even though my machine's at 8 megahertz, he's got his running at 4 megahertz, and the music's sounding reasonable. Anyway, so how do we set up that delegate array? So first thing we do is we've got this array of delegates, and it's one for each byte of a possible instructions, so 0 through 255. And we start by assigning them all to a not implemented function, so that all 256 slots in our array will jump to not implemented. And if we go and have a look at not implemented, you'll see it's basically a sort of a controlled crash. Let's go have a look at that. So not implemented just writes out a message saying this instruction is not implemented, and then die with a 0A, which means not implemented in the hopper error codes. But at least you get a message to the serial port telling you which instruction was not implemented and at what address in your program it was first encountered. Like, there we go. So not implemented at this address. Anyway, so that's how not implemented is working. So we populate our array so that we'll fail gracefully if there's an instruction we haven't implemented. And then we did a whole bunch of playing to get to count timing. Like if you're going to make a timing loop that simply decrements a counter to 0 and then jumps out. So first time how long it's going to take, measure the elapsed time, start there, subtract how many milliseconds does, this is like some arbitrary number of loops, like 1,000 loops. How many milliseconds does 1,000 loops take? And then you get the, now you can say how many microseconds does each loop take. And then you can use that to make little loops to do the timing. And it's a slight problem with the hopper interpreter because the smallest time, the actual function call takes longer than what the loop would take. But for most of them, it works pretty well. And then here we assign the operations. So like we've got a wait instruction. We put it to where the constant for wait is. We put wait send into the send instruction, end into there. We put wait into the slot in the array where wait should be. And we've got a 16th instruction, which is just another wait kind of instruction. And we put that in the slot. And then this N1 instruction is the most complicated one. It's 16 possible different delays, of which when you're running on the fast clock speed, you can just have a single N1 instruction. When you're running on the slow one, we had to try and this is all done with loops. The fast one I'll show you is done differently. So, and the fast one is the kind of better, cleaner code. And it's designed to run not just on the 6502, but also on the Raspberry Pi Pico. So on the fast one, it just says of these possible 0 to 15 plus 1 to 16. I must, how many delays must I do for that? And we measure the cost of what an empty call here would be. And this is the empty call that we use for calibration. Do nothing, right? And then we subtract that from the number of samples and delay for that. But now this is tricky. Why are we delaying for samples, right? So in the standard, the VGM standard, a sample is 22 microseconds. And so to avoid doing any multiplication in this little delay loop, which is really tight, I just do the subtraction. Subtract, if the cost of this call is greater than the actual number of samples, the cost of the call in samples, in other words, the cost of the call in multiples of 22 microseconds, if the samples is greater than that, then we'll delay for the remaining samples. And so some time will be taken up by the actual function call and the remainder by the delay function. Now, the delay was based on the Arduino delay, which is in milliseconds. And I didn't want to add more APIs, and I didn't want to add a second timer to the minimal runtime because it'll be big. There's no room for it. And because, the complexity of adding a second timer. So instead of doing that, I did this sneaky thing. I changed the APIs so that there's an extra little bit of trickery here. So what it has is it has this API now. So you can tell the Hopper runtime, by default, the number of microseconds in a sample is 1000. And that means you'll get the behavior like the Arduino. So if you say delay for one sample, it delays for 1000 microseconds, which is 1 millisecond. So delay 1 would be 1 millisecond by default. Delay, 60 milliseconds, that sort of thing. So delay 60,000 a second. So now I just made it so that you can arbitrarily set the samples for the delay function. And this one here is a constant. If we look where it's defined, I right-clicked on it, it's 22 microseconds. So I changed the delay API to work in VGM's, video game music samples as its unit. So its unit is now 22 microseconds, which means I can just really easily write this player. So it really simplifies writing the player, and for multiple platforms as well, because microseconds are microseconds no matter which platform you're on. So on the Raspberry Pi Pico, for example, you just use exactly the same code. And that's how it works. So let me compile this. And then we'll upload it to the device. F5 to get it onto my device. There we go. It's uploading onto my my 6502 machine. And now, because on my microphone that I'm doing this recording on, I've got filtering on, and I don't really have a microphone to record what's in front of the camera. I'll just cut out of here while I quickly play the Sonata on my machine. It should sound very, very similar to the bit that was at the beginning of this video that was being played on, that was recorded by Dave. So let's see what it sounds like. There we go. I'm pretty sure Mozart's turning in his grave somewhere. Anyhow, what Dave did to play more music on his machine is he used his X modem and his banked RAM to load up full tunes into his RAM. And I just don't have that kind of capability on this device at all. So, but I will use this as an opportunity to demonstrate the sort of cross-platform nature of Hopper. So this is a Raspberry Pi Pico clone, and I made another little sound card that's easier to work with the same chip. And let's go have a look what that looks like on the Raspberry Pi Pico now. So I've got another program here. Let's go have a look. This is all on the GitHub repo, by the way, under the samples folder. So I've got something called VGM Player as opposed to VGM Demo. And what have I done in this program? I've got an outer loop. I do a directory. I open the directory of a subfolder on the Raspberry Pi Pico called samples. I iterate through that folder, finding the tracks which have an extension of VG. And then I list them out. And if you press a key between 0 and 9, I treat that as a play the track key. And if you press escape or control C, I break out. So if you 0 and 9, it falls through to here, picks up the file path for the track, and then uses a very similar player that we just saw in the other program. And that player, in a single instruction, will, with this read instruction, and I've made it slightly bigger than 8K buffer. because you might, when our converter appends an end on the end, if there wasn't one. And in a single instruction, it loads from the file straight into that buffer, and then assigns it to the one that's being used by the player, and then runs that tiny loop to play again. So the code for this loop is very much the same as the code we were using on 6502. The initialization code is identical. Let's build this. Let me plug in my RP2040. Oh, very noisy when it's turned on and not initialized. Let's do that. Turn it off. Okay, I've compiled it. And now I'll upload it. And then let's run that. Right. So you get the idea. That's done the directory of my files, and it's ready to play it. And once again, I'm going to cut out to another video that I made of playing one of these because my microphone setup's just not set up to record something without filtering out the whole track. So I just recorded on my phone. So let's do that. I think I'll press 1 here and play that. All right, pretty cool. So that is what it sounds like on the RP2040, running exactly the same code. But I've skipped a section. I skipped a bit here, because the RP2040 device has features here that we don't have yet on the 6502, which is the whole file system that we have here. So we've got, directory APIs. Let's Control C out of there. So let's go back and have a look at that. So yeah, we've got right click on that, directory APIs. They look very similar to C# directory APIs, but with slight, some little differences. And there's a directory object in Hopper, and then corresponding file APIs with the file object that you can read and stuff. And then there's some utility functions in a path file that is very similar to C# path object in C#. But I still missed something. It's like, how on earth does my Raspberry Pi Pico, how does this little device here, how does it have files on a folder called samples? Well, that's about the Hopper monitor. And these APIs do exist. You can get to them from your programming too. But the easiest way is to use the Hopper monitor. So if I look in the Hopper monitor and I press question mark for help, there's a transfer function here called T. And if you use the transfer function and your arguments, so I can say, transfer, and I can put in a file name here and then a folder here, like that. So, samples. So we could probably just do one actually. Let's just go out and go to samples folder. It makes it easier. Do a dir. Got a couple of samples, so let's the bells one, for example. So I can do hoppermon transfer bells.vg to samples, and then it'll upload that to a folder on my flash drive. So there it says uploaded samples bells.vg 8K. So the way this works is that by default, when you install Hopper on your microcontroller, which you do from, if you go to GitHub and you go to releases here, let me switch to that screen quickly. So if you go to releases on GitHub and then if you scroll down, the way you put Hopper onto your Pi Pico is you drag and drop either the Pico or the Pico W UF2 file onto the device, and this is programmed such that on your device it'll use a lot the majority of the built-in flash on your device as a drive, so a disk system. So automatically Hopper will have a file system on your Raspberry Pi Pico device, so you can upload all the music. All right. yeah, I'll put some links in the description to Dave's machine, to the VGM resource online that we rip all these tracks from. Um, yeah, and yeah, I should put something to how you wire up one of these serial, like how you do the wiring for one of these. Um, yeah, Dave's schematic for his board is probably the best for that. But I'll see if I can find another one as well, and I'll put a link up to that in the description as to how you do the music. Anyway, um, thank you for watching and learning about VGM, which I didn't know about last week either. So kind of fun to do something useful, to like do something useful with the 6502's parallel port and play some music on it. Yeah. Cheers.